Hello everyone and welcome to today's presentation. We are excited to explore the fascinating world of eigenvalues and eigenvectors. These fundamental concepts in linear algebra have application far beyond the classroom, spanning science, engineering, and data analysis, and even areas like finance and machine learning. Before we dive in, let me introduce to our team. I'm Liang Yu Hao, and with me are my friend Heng Fok Sang and Yong Jia Ken. By the end of this presentation, we hope you will not only understand what eigenvalues and eigenvectors are, but also appreciate their power and versatility, whether it's analyzing physical system, processing large set of data, or predicting the behavior of dynamic system. Eigenvalues and eigenvectors are everywhere in our life. Now, to kick things off, let me hand it over to my friend Yong Jia Ken, who will introduce us to the basic concept behind these fascinating ideas.
Thank you, Yuhao. Let's start by answering the key question, which is, what are eigenvalues and eigenvectors? So, eigenvalues can be thought of as the magnitude of change in a linear transformation. Imagine you have a set of vectors and you perform some kind of transformation on them, such as scaling, rotating, or stretching them. During these transformations, certain vectors may not change direction at all. They might stretch or shrink, but they keep pointing in the same direction. The scalar by which these vectors are stretched or compressed is called the eigenvalues. In other words, eigenvalues are scalars that indicate how much a vector is scaled during a transformation. If an eigenvalue is greater than 1, it means the vector is stretched. If it's between 0 and 1, it's shrunk. And if the eigenvalues is negative, the vector not only gets scaled, but also flipped in the opposite direction. And the second question will be, what are eigenvectors? And so eigenvectors are special vectors that remain aligned in the same direction during a linear transformation. While the transformation may change the length of these vectors, their direction remains unchanged. This unique property makes eigenvectors incredibly useful in analyzing the structure of matrices or transformations. Together, eigenvalues and eigenvectors reveal the underlying structure of linear transformations. They simplify the analysis of systems and allow us to break down complex transformations into more manageable pieces. Now that we understand the basis, let me pass it back to Yuhao, who will delve into the exciting real-world application of these concepts.
Thank you, Jagan, for breaking down these fundamental concepts. Now that we have a foundation, let's explore how eigenvalues and eigenvectors are applied in various fields. Their power lies in simplifying complex systems and providing critical insights into their behavior. First, the matrix diagonalization is one of the most important applications of eigenvalues and eigenvectors in linear algebra. Diagonalization is the process of transforming a complex matrix into a simpler diagonal matrix, where all non-diagonal elements are zero. This is particularly useful because diagonal matrices are much easier to work with when performing mathematical operations like exponentiation or inversion. In fields like physics, diagonalization is used to solve problems in quantum mechanics. For instance, the energy state of system can often be found by diagonalizing an Hamiltonian matrix, which represent the total energy of the system. By simplifying the matrix, diagonalization allows physicists to more easily compute the eigenvalue which correspond to the possible. Besides, eigenvalues and eigenvectors are also incredibly useful when it comes to solving systems of linear equation. In particular, they allow us to understand the nature of solution to this system. For example, if all the eigenvalues of a matrix are non-zero, it means that the system has a unique solution. On the other hand, if one or more eigenvalues are zero, the system may have infinitely many solutions or no solution at all. In practical, in practical terms, when engineers or scientists model real-world systems using linear equation, they rely on eigenvalues and eigenvectors to determine whether the system is well posed and whether the solutions are stable. This is critical in areas like structure analysis, where solving large systems of equation is a daily task. After that, stability analysis is also another key area where eigenvalues shine. In dynamic systems, such as those found in mechanical engineering, robotics, or even economics, eigenvalues can help predict long-term behavior. In engineering, for example, if a system eigenvalues have large positive values, it may indicate that the system is unstable, meaning small perturbations can cause large deviations in system output. Conversely, if the eigenvalues are negative or have small magnitude, the system is considered stable, as it will return to its equilibrium state after a disturbance. This type of analysis is essential in fields like control theory, where stability determines whether a system, such as an autonomous vehicles, can operate safely under different conditions. Okay, now that we've seen more general application, let me hand over to my friend Fuk Sang, who will guide us through specific practical application in fields like mechanism engineering, and, machine learning.
Thank you, Yuhao, for explaining the key application of eigenvalues and eigenvectors. I am Fuksang. Now I am going to talk about the practical application of eigenvalues and eigenvectors. Let's take a closer look into some real-world application where eigenvalues and eigenvectors help solve complex problems and optimize performance across various industries. First is the application in quantum mechanics. Quantum mechanics is a field that deals with the behavior of particles at the atomic and subatomic levels. Here, eigenvalues and eigenvectors are indispensable tools. In quantum mechanics, the state of a quantum system can be represented by a set of eigenvectors. The corresponding eigenvalues represent observable physical quantities like energy, momentum, and angular momentum. The next is the application in structural engineering, which eigenvalues and eigenvectors play a critical role in model analysis. This type of analysis is used to predict the natural frequencies at which structures such as buildings or bridges will resonate. Resonance can be dangerous, especially in earthquake-prone regions, as structures can collapse if they resonate with the frequency at seismic waves. By analyzing the eigenvalues of a structure's stiffness matrix, engineers can determine its natural frequency and design structures to avoid resonant frequencies during an earthquake. Eigenvectors, on the other hand, help define the mode shape of the structure, showing how different parts will move under certain loads. The information is invaluable in designing earthquake-resistant buildings and bridges. The next is the application in image processing. Eigenvalues and eigenvectors are also widely used in image processing. One of the most notable applications is in facial recognition, where eigenvectors, often called eigenface, are used to identify and classify facial features. By applying a technique known as Principal Component Analysis (PCA), facial images are transformed into a lower dimensional space, where the most important features of the face are captured by eigenvectors. These eigenfaces form a basis of comparing new images to those in a database. Eigenvalues help in determining which features are most significant, thus allowing for quick and efficient recognition. This technology is not only used in security systems, but also in social media platforms and smartphone cameras for identifying faces. The next is the application in control system, such as those used in robotics or automation. Eigenvalues are crucial for determining the stability of the system. Engineers design controllers to ensure the system behaves in predictable and stable manner. By analyzing the values of the system's state matrix, they can assess whether the system will convert to a desired state or divert over time. For instance, in autonomous vehicle, control systems rely on stable eigenvalues to maintain balance, directions, and speed. Eigenvectors play a role in defining the control strategies that ensure smooth and safe operation, even in complex environments. The last is the application in Principal Component Analysis (PCA). Principal Component Analysis (PCA) is a widely used data analysis technique, especially in fields like data science and machine learning. PCA reduces the dimensionality of large datasets by identifying the directions eigenvectors in which the data varies the most. The eigenvalues associated with these eigenvectors indicate the amount of variance captured by each component. PCA is used for tasks like data visualization, noise reduction, and feature selection. For example, in genomics, PCA helps analyze large datasets by identifying patterns in gene expression, making it easier to understand complex biological process. Similarly, in finance, PCA is used to identify key factors that influence stock market behavior. This is the practical application of eigenvalues and eigenvectors. Now, I will pass my speech to Jiaken to make a conclusion.
Thank you, Fuksang. To conclude, eigenvalues and eigenvectors are not just abstract mathematical concepts. They have a wide range of practical applications across many fields, from quantum mechanics to structural engineering, from image processing to control systems. These tools provide deep insights into the structure and behavior of systems. Looking forward, as computational techniques continue to advance, our ability to handle large-scale data and complex systems will only grow. This means that eigenvalues and eigenvectors will become even more critical in solving emerging challenges in fields like quantum computing, artificial intelligence, and big data analysis. In the future, we can expect to see new algorithms and techniques that leverage the power of eigenvalues and eigenvectors to address issues such as computational complexity and noise sensitivity. As our understanding deepens, these concepts will continue to drive innovation in science, technology, and engineering. Thank you all for your attention, and we hope you now have a clearer understanding of the power and potential of eigenvalues and eigenvectors.